Okay, welcome to our lesson, and we are learning today about refraction of light. This one is is the third topic about light that you have or we have studied so far. In Form 1, we learned about rectilinear propagation of light. In Form 2, we learned about reflection at the curved surfaces or the curved mirrors. In Form 3, we are now learning about refraction of light, and in Form 4, we will learn about thin lenses, which is a topic dealing with light. Welcome. I hope you will enjoy the lesson. Now, in each topic that we always study, there must be objectives to be made. It is you to decide whether you will meet those objectives or not. Now, look at this one. By the end of this topic, the learner should be able to describe a simple experiments to illustrate refraction of light. State the laws of refraction of light, the two of them. Verify Snell's law using an experiment or experimentally. Define refractive index. Determine experimentally the refractive index of a substance. Describe experiment to illustrate the dispersion of white light. Explain total internal reflection and its effects. State the applications of total internal reflection. Solve numerical problems involving refractive index and critical angle. So what is there is this. These are the objectives. And in fact, after you have been given objectives like this one, now you can go alone and discuss one by one. Do you know to verify Snell's law? Do you know to calculate? All those. But because we are so much lenient and we are so much generous, I will take you through the slides describing all these objectives, making sure that you meet all the objectives. These are what we are going to see. We are going to see refraction of light. This is now the content that we are supposed to cover. Refraction of light, which includes the laws of refraction. We go ahead and we determine the refractive index in we have 4 ways of determining refractive index. We have the Snell's law, which is famously known as sin I over sin R. We also have using a real and apparent depth. And we use velocity of light. And lastly, we will use the critical angle to determine refractive index of a substance or of a material. We are also going to see the dispersion of white light, total internal reflections and its effects, then applications of total internal reflection, that is the periscope and the optical fiber. And in this we will also see why we prefer prisms over mirrors. Then we do some few calculations here and there on critical angle. Let's start from there. First of all, I want us to define the term refraction of light. We defined the term reflection of light as the bouncing back of light when it hits a shiny surface. There are people you will never know whether they are talking of refraction or reflection. They put your R and R, but no problem, we will understand. In such a scenario, we work with what you write, not what you say. So, refraction of light refers to the change in direction of light at the interface as it travels from one medium to another at an angle. There are two terms there. At the interface, at an angle. If you forget one of them, you will not score. Just imagine if you forget the two of them. So now, for example, look at this. We have air and we have water. Of course, the two are different materials. Air is different from water. So the light is traveling from air to water at an angle. If I say at an angle, I mean the direction, or I mean the way light is entering or getting through the media or the boundary, the interface, that is not normal. That is, it is not at 90 degrees. It's not perpendicular at an angle. Then the light will bend. If you try to allow it get at the interface normally, then there will be no refraction. The light will not bend. It will pass and deviate it. Now here, we have three terms I want you to see. We have incident ray, normal line, and refracted ray. Here. So the angle between the normal and the incident is called the angle of incidence. The angle between the normal and the refracted ray is called the angle of refraction. The angle of incidence is denoted by letter I, and the angle of refraction is denoted by letter R. Get that very well. This is what I was saying. Check on my screen. A ray that travels perpendicular, the other name for perpendicular is normally, to the interface, proceeds across the interface, not deviated, since the angle of incidence to the normal is 0. Get that one clearly. Now, I want us to see like 4 case examples that happens because of refraction. There are things that happens simply because of refraction. The first one is when you put a stick in water, it bends. Hey, it appears to be bent. The stick will never bend. Sorry for that. It appears to be bent. Why? Because of refraction of light. We will still see this. A coin in a beaker of water appears near the surface than it actually is. I told my students to come with 20 shilling coin each, so that we can perform the experiment. And after that, I will not give you back the 20 bob. Up to today, we have not performed the experiment. If you can hear me wherever you are, when we meet, please come with that coin. We put in a beaker. Then we see whether the coin has been raised. And after that, don't ask me about the coin. C. A pool of water appears more shallow when viewed more obliquely. Yes, and if you have a swimming pool in your school, not a must to be in your school, any swimming pool around, just go and see. When you view it normally, it appears as if it's very shallow. Only the swimming attendant will tell you this place is 9 feet, yet it appears to be 2 feet. You can die there easily. Now that most of you people don't know how to swim, please, if there's something that you need to know in this world, the first one is know how to swim before you know how to cycle. Where do you get the guts to learn how to drive, cycle without knowing how to swim? Anyway, Nisawa. Now, there is something called optical density, and I'm going to differentiate between optical density and physical density. You see now, light will pass through media in different velocities. When the medium is denser, it will pass with a very slow speed. But now, the physical density, we know that water is denser than maybe paraffin. Sometimes it does not work here. Though, in most cases, the materials which are optically denser which are physically denser, are also optically denser. But we have some few case examples. Water and paraffin, we know that water is denser in a physical density. It is denser than paraffin. But in terms of optical density, paraffin is denser than water. Meaning, light will find a higher time passing through paraffin than in water. So a ray of light traveling from an optically less dense medium to an optically denser medium bends towards the normal after refraction. I will explain that. And when it is moving from a denser to a less dense, then the ray of light will be refracted away from the normal. I will explain here. Look at these two. From air to glass, it means the light is moving from a less dense to a denser. So the refracted ray will move towards the normal. Towards the normal. Towards the normal. This one, it is moving from glass to air, away from the normal. It moves away from the normal. Now, my point is here. Some media are physically denser, but optically less dense than others. Kerosene is physically less dense, but optically denser than water. I hope you are getting what I'm talking about. There's an exercise there, and anytime you see an exercise, it's not for me to do it. I cannot do an exercise. I did mine. So exercise belongs to the student, not the teacher. There are some of you are expecting me to define the term refraction, who are expecting me to draw the diagram to show the refraction of for a ray of light across the following boundaries in the order they appear. No. That's you. You will do it, because if I do it, then I will be babysitting you, and which I really don't want. So this is your exercise. Please attempt. Yes. This one is still your exercise. The figure below shows how refraction occurs. Which of the two media is optically denser? You simply compare I and R. The smaller one is the denser one. Explain with the help of a diagram why pencil placed partly in water appears spent. Please, a very simple thing. Please do that. Now let's move on. This is another main objective of this lesson: laws of refraction. Laws of refraction. Is there a difference between a law and a principle? Anyway, find it out. The incident ray, the refracted ray, and the normal line all lie in the same plane at the point of incidence. That one is also applied in reflection of light. So you just need to change the word refracted to reflected. The law number 2, we also call it the Snell's law. And please, when you are asked to give them in that order. It states that the ratio of the sine of the angle of incidence, that is the I, to the sine of the angle of refraction, that is R, is a constant for a given pair of media, that is sine I over sine R. The constant is called refractive index. So when you are also told to divine or what is refractive index, you give us the Snell's law. One answer, 2 questions. If they ask Snell's law, that is it. If they ask the refractive index, do you? But now, there is somebody there, ajui maana ya for a given pair of media. Kama ni wewe, I don't know, just smile. For a given pair of media, it means if the light is traveling from glass to water, and the angle of incidence is 30, and the angle of refraction is 25. Sine 30 over sine 25 will give you a given value, which is a constant, which is a refractive index. The same pair. Now you change the angle of incidence from 30 to 35. Of course, the angle of refraction will increase, maybe 29. Sine 35 over sine 29 is supposed to give you whatever you quote earlier by having sine 30 over sine 25. Even if you go to sine 40 over sine 35, maybe 35 is the angle of refraction. As long as you are dealing with glass to water, you are supposed to get a constant value. Yes, and that's what we are going to, when we get to plotting of graphs, that's what we are going to get. It is here. A graph of sine I against sine r is a straight line passing through the origin, and the slope of the graph gives the refractive index of a material. I have nothing much to explain there. Slope means the gradient, which is change in y over change in x. I believe you know how to plot a graph until you get the 5 required marks. First mark is axis, just drawing a y-axis and the x-axis, and you label what does each axis stands for. Like in this case, it is sine I, sine r. That is 1 mark. If you had gone to the exam room to pick 1 mark, just to do that, x and y-axis, sine I, sine r, go. But if you want more marks, look for the next 1 mark is scale. Look for a good scale that will accommodate better part of the graph, 3/4, that is. Then you put some values on the y-axis and on the x-axis. From there, you have 2 marks. The other 2 marks comes from plotting. You just put points. You see the point. You bring together y. I mean sine I over sine x. Where did they meet? Put the x or a dot with the circle in it. That is 2 marks. Now, when you put the line or a curve, you get another mark. Those are 5 marks. Very simple way of obtaining plotting a graph. But also, I can advise you, just in Ambassador Foundation YouTube channel, there is a lesson on plotting of graphs. I did it very well, so you can just go and search plotting of graphs. Yes. So now, definition of refractive index. I said it earlier. It's like the definition of Snell's law. Now, what is there is this. When the ray is traveling from medium 1 to medium 2, this letter that looks like N but not N is used to denote refractive index. For example, now in this case, I've written here 1 and here it's 2. Somebody who knows physics like you and I will know that the light was traveling from medium 1 to medium 2. Alternatively, when it is written this way, you can say it is the refractive index of light traveling from medium, it is the refractive index of medium 2 with respect to medium 1. That is my point. Even if the light is reversed back, it will follow the same path. We call it the principle of reversibility of light. A ray traveling from medium 2 to medium 1 along the same path is refracted, making the same angles. The principle of reversibility of light. Now, let's dwell here for some few minutes. Then I want you to connect all the lessons in this particular topic. It may not be one continuous video, but after this, find the next one. I will indicate for you refraction of light 1. That means the first video. The second one is refraction of light 2. And that way. So what this actually is? Look here. Just look at it very well. Medium 1, medium 2. The light is traveling from medium 2 to medium 1. So if you take sine r over sine I, it will be the refractive index of medium 1 with respect to medium 2. If you take sine I over sine r, it is going to be refractive index of medium 2 with respect to medium 1. It is the inverse of the other one. If you get the refractive index of light traveling from medium 1 to medium 2 by having sine I over sine R, if you want to get the opposite, you simply do the reciprocal. You don't have to do a lot of things. You simply do the reciprocal as shown in this particular part. There is this term that I want you to know. Absolute refractive index is the refractive index of a material with respect to a vacuum. Vacuum means, okay, it can also be with respect to air, but in most cases we use the word vacuum, but it is with respect to air, because we always compare it to vacuum, because vacuum has a refractive index of 1. And by the way, refractive index has no units, simply because it is a ratio. Yeah, that is it. So now, this is an example which I want you to do it, then check. I will show you the workings in my next video. Just finish this and then check the next one. Thank you. That was the introduction of refraction of light. Continue watching. May God fulfill your dreams.